This animation of a stone fortress that fractures and dissolves into dispersed digital data nodes visualizes a structural failure in network engineering. The physical perimeter that once defined digital security no longer exists. Historically, security architecture operated on a localized castle and moat strategy. Specialized hardware like switches and routers managed packet flow inside a centralized data center, while strict firewalls inspected all traffic at the physical boundary to block external threats. That physical boundary collapsed under the weight of modern computing protocols. The rapid adoption of remote work, combined with data migrating to software-as-a-service platforms, means the bulk of corporate operations now occur entirely outside the data center. This map displays the resulting architectural problem. Highly distributed remote users are requesting data from external cloud servers. But legacy network models still attempt to route those chaotic traffic lines back to a central hub for inspection before sending them back out to the internet. Forcing cloud-bound traffic to detour thousands of miles to a central firewall creates severe latency. The infrastructure meant to secure the connection actively degrades the performance of the application. Resolving this requires applying the concept of defense in depth across the entire Open Systems Interconnection, or OSI, model. Engineers must evaluate vulnerabilities from the localized hardware switches at Layer 2 up through the application protocols at Layer 7. Securing a distributed enterprise means rebuilding defense mechanisms from the physical internal hardware out to a cloud-native framework known as Secure Access Service Edge, or SASE. Modern network security cannot rely on thickening a localized perimeter wall. It requires engineers to redesign exactly where and how trust is granted at every individual layer of communication. The foundation of internal defense begins on the local network floor with Layer 2 switches. These devices govern communication within a local area network by forwarding data frames to specific Media Access Control, or MAC, addresses assigned to individual endpoints. Layer 2 protocols were designed for efficiency within an enclosed system, assuming that all connected devices are trusted. This trust-based architecture makes internal switches highly susceptible to manipulation if a compromised device connects to the network. This diagram illustrates an Address Resolution Protocol, or ARP, cache poisoning attack. ARP maps IP addresses to MAC addresses. Because the protocol accepts gratuitous replies without verification, a rogue node can broadcast a forged response, linking its own MAC address to the IP address of a legitimate gateway. This forces the victim device to send all its traffic directly to the attacker, establishing a man-in-the-middle intercept. Defeating this requires strict port-level mitigation. Administrators deploy DHCP snooping, which filters inbound traffic and only permits server responses on trusted uplink ports. This process actively records valid configurations into a verified binding table. Once that baseline is established, Dynamic ARP Inspection utilizes the binding table to scrutinize every ARP packet. If a device sends an ARP response that does not match a verified IP to MAC mapping, the switch instantly drops the payload. Moving up to Layer 3, routers serve as the dispatchers between disparate networks. Their primary boundary defense is network address translation, which replaces the private IP addresses of internal devices with a single public-facing IP, effectively masking the internal topology and restricting unsolicited inbound connections. This diagram shows a router utilizing virtual routing and forwarding, or VRF. A single physical device is internally divided into multiple isolated routing tables, keeping specific traffic streams strictly segregated by department or function. By logically isolating departmental data, VRF creates hard internal boundaries. If an attacker breaches a workstation in one segment, the router prevents them from moving laterally into more sensitive network tiers. Routers also require internal protection for their own processing power. Control plane policing applies strict quality of service filters that rate limit suspicious traffic destined for the router's CPU, preventing denial of service attacks from crashing the device's ability to manage routing protocols. Before localized hardware can reliably filter traffic for the wider organization, it must first survive attempts to compromise its own routing tables and ARP caches. Once the localized network is hardened, engineers face the challenge of remote access. They must project this secure internal fabric across the public internet to reach unmanaged employee devices. The historical standard for this is Internet Protocol Security, or IPsec. Operating at Layer 3, IPsec is a comprehensive suite designed to encrypt all IP traffic flowing between two endpoints, regardless of the specific application generating the data. This diagram breaks down how IPsec operates in tunnel mode. The protocol completely encapsulates the original IP packet, including its routing header, inside a brand new external IP packet. This process ensures the internal network topology remains completely hidden while traversing public infrastructure. This architecture relies on two distinct phases. The Internet Key Exchange establishes a secure, bidirectional management channel to negotiate security associations, while the encapsulating security payload provides the actual cryptographic scrambling of the transferred data. While highly secure, IPsec carries heavy administrative overhead. It requires dedicated client software installed on the end user's machine, and because it relies on specific protocol designations like UDP port 500, IPsec traffic is frequently blocked by public or restrictive hotel firewalls. Transport Layer Security, or TLS, offers a stark operational contrast. Operating at Layer 7 of the OSI model, modern TLS VPNs do not attempt to encrypt the entire network segment. They only secure individual application-specific web sessions. This diagram compares the two traffic flows. An IPsec packet fails against a strict firewall rule set, while the TLS session smoothly traverses the barrier. Because TLS operates over standard TCP port 443, the exact same port used for everyday web browsing, it rarely requires custom firewall configurations and functions seamlessly directly within a user's web browser. This accessibility carries a performance penalty. Running a TCP-based application inside a TCP-based VPN tunnel creates a redundant processing loop known as the TCP over TCP effect, which increases processing overhead and degrades transmission speed compared to IPsec. Selecting a remote access protocol is a strict engineering compromise. IPsec provides broad, hardware-level network control, while TLS sacrifices total network coverage for highly granular, frictionless user access. Securing the transmission tunnel is only the first step. The data packets emerging from those tunnels must be actively inspected before interacting with internal systems. A traditional static firewall assesses traffic strictly by checking Layer 3 and Layer 4 metrics, such as IP addresses and port numbers. It acts as a rudimentary gatekeeper, but cannot examine the actual contents of the packets it allows inside. This diagram illustrates a linear service chain designed to solve that limitation. After passing the initial static firewall filter, the data packet enters an Intrusion Prevention System, or IPS. Here, the system performs deep packet inspection, actively scanning the data inside the allowed connection. Positioned in line with the traffic, the IPS cross-references packet payloads against a database of known exploit signatures and behavioral baselines. It identifies and drops network-level threats, like port scans or brute force attempts, in real time. However, an IPS evaluates data at the network and transport layers. It lacks the architectural context to understand complex web application logic, rendering it entirely blind to threats embedded within encrypted HTTP payloads. To cover this exact vulnerability, engineers place a Web Application Firewall, or WAF, further downstream. The WAF operates exclusively at Layer 7, engineered specifically to scrutinize web-facing applications and APIs. Because it operates at the application layer, the WAF can terminate the SSL or TLS encryption. It unpacks the raw HTTP request, evaluates query strings and post bodies against expected formatting, and blocks logic-based attacks like SQL injections that mimic legitimate user input. An IPS cannot read web logic, and a static firewall cannot read packet payloads. Defending a perimeter requires chaining these specialized tools together, because each inspection layer is structurally blind to the threats operating at the layer above it. Pacing slightly faster. When we apply this complex, hardware-heavy inspection chain to the geography of a modern enterprise, the architecture hits a critical breaking point. This map demonstrates the tromboning effect. A remote user initiates a connection to a public cloud application. Because the organization's IPS and WAF hardware live in a localized data center, the traffic must travel thousands of miles out of its way just to be inspected, before finally routing back out to the cloud provider. Routing traffic through a localized physical choke point introduces massive delays. This latency instantly degrades time-sensitive data protocols, rendering voice-over IP and video conferencing tools unstable and inefficient. Attempting to solve this by purchasing and maintaining a dedicated stack of localized firewalls and IPS hardware for every single remote branch office is both financially unscalable and an administrative nightmare. The localized data center model collapses under cloud environments. Relying on centralized physical hardware directly violates the geographic efficiency required to route modern, distributed network traffic. Resolving the latency dilemma requires Secure Access Service Edge, a cloud-native architecture that merges software-defined routing with distributed security inspection. This interface illustrates the networking foundation of SASE, software-defined wide-area networking. SD-WAN abstracts the network control plane and dynamically steers traffic across multiple concurrent transport links, including broadband, MPLS, and cellular networks. The SD-WAN controller continuously tracks jitter, packet loss, and latency across all available connections. It automatically routes highly sensitive data over the most stable links, while offloading bulk transfers to cheaper connections, completely eliminating the static routing bottlenecks of legacy networks. While SD-WAN optimizes the geographic path, the Security Service Edge component migrates the physical hardware inspection stack directly into decentralized, cloud-delivered nodes positioned globally near the end users. This cloud transition allows engineers to replace the broad access of standard VPNs with the strict enforcement of zero-trust network access. This diagram shows ZTNA actively intercepting a connection. It removes the concept of implicit network trust entirely. The system verifies the user's identity and confirms the security posture of their physical device before granting a microtunnel connection to a single specific application, rather than the entire internal network. Zero Trust integrates directly alongside cloud access security brokers, which monitor SaaS platform usage, and firewall as a service, uniting discrete inspection tools into a single automated cloud policy engine. Natively combining SD-WAN routing with cloud-delivered security inspection eliminates the manual configuration of complex IPsec tunnels between branch locations, drastically reducing the administrative errors inherent in disaggregated hardware stacks. Enterprise defense began by guarding physical switch ports and routing tables inside isolated, climate-controlled rooms. It has evolved into deploying dynamic, identity-based zero-trust policies across a global public infrastructure. True modern network defense unites intelligent, latency-aware packet routing with continuous identity verification. By abstracting security away from localized hardware, engineers create a resilient ecosystem capable of protecting data entirely independent of physical borders.
Welcome to this explainer. You know, if you really stop to think about it, the modern internet is honestly kind of a crazy paradox. On one hand, it is a literal war zone out there. We are talking about malicious bots, highly sophisticated application exploits, and massive volumetric data floods hitting networks every single second. Yet, on the other hand, your favorite web applications still manage to load in absolute milliseconds. How is that even possible? How does an app survive a massive digital bombardment without sacrificing an ounce of speed? Well, today, we're going to unpack the architectural secrets that make this all happen.
Okay, so here's our game plan for today. We're going to map out our journey into this high-tech digital fortress. We'll start with the modern digital battlefield, look at edge speed and shields, talk about filtering the application layer, figure out how to stop the thundering herd, secure our cloud VPCs, and tie it all together with a unified defense in depth.
All right, part one, the modern digital battlefield.
So the fundamental shift in digital infrastructure over the last few years has been absolutely massive. We've completely moved away from those localized, single-point data centers to these hugely distributed global networks. And in this new paradigm, the boundary between the wild public internet and your internal network is the new battleground. Which brings us to a really core question. How does digital infrastructure actually use defense in depth to stay incredibly fast while it's constantly under attack? Historically, IT teams thought of security and performance as a strict trade-off. If you wanted deep security inspection, you had to add latency. If you wanted blistering speed, well, you bypassed the heavy filters. But as we're going to see, modern architecture has completely unified these two concepts. Speed and security are now the exact same mechanism.
Moving right along to part two, the edge, speed and shields. This is literally your first line of defense, the content delivery network, or a CDN. By placing points of presence all over the globe, CDNs cache content geographically closer to the users. This not only slashes latency, but it acts as an enormous shock absorber, filtering out malicious traffic and soaking up massive DDoS attacks before they ever even get close to your core infrastructure.
Now, the mechanism that makes this global absorption possible is just incredibly cool. Think about traditional unicast routing. Basically, one IP address equals one specific location. That's a massive bottleneck, right? It's highly vulnerable to being overwhelmed. But with anycast routing, that exact same IP address maps to multiple global locations. So during a DDoS attack, anycast naturally distributes and dilutes that malicious traffic across your entire global footprint, rather than letting a single bottleneck get totally crushed.
And the absolute magic making anycast work is BGP, or the Border Gateway Protocol. This protocol automatically directs client traffic to the topologically nearest healthy node that actually has processing capacity. What this means in real life is seamless automatic failover. If a massive attack actually does manage to knock a specific data center offline, BGP just updates the paths. Traffic instantly and automatically reroutes to the next closest node. And it does it all without a single human having to intervene.
Okay, that brings us to part 3, filtering the application layer.
So those big brute force volumetric attacks, they've been absorbed at the edge. But what happens when smarter threats perfectly mimic legitimate user behavior? I'm talking about layer 7 threats. Things like SQL injection, cross-site scripting, malicious API calls, and automated bad bots. These look like completely valid web requests, so traditional network firewalls just wave them right through. And this is exactly what the Web Application Firewall, or WAF, is actively hunting for. Sitting right at the edge, the WAF inspects the actual payload and the headers of every single incoming web request, specifically looking for these sophisticated anomalies. There's a saying that traditional network-level block lists are completely ineffective against application layer attacks. And honestly, it's so true. We just can't rely on blocking IP ranges anymore. We have to lean on intelligent bot management, using machine learning and behavioral analysis to challenge suspicious requests with things like CAPTCHAs or JavaScript checks. Plus, the edge handles TLS termination. That means it takes on the heavy computational load of encrypting and decrypting HTTPS traffic, so attackers can't just exhaust your origin server CPU with bogus cryptographic handshakes.
All right, part 4, stopping the thundering herd. Let's step past the edge and into the intermediate moat of our fortress.
Picture this. A highly popular image or video on your site suddenly expires from the CDN cache, right in the middle of a huge traffic spike. Suddenly, you have 50+ edge servers all around the world experiencing a cache miss at the exact same second. This massive spike can trigger what engineers call a thundering herd. All 50 edge nodes turn around and request that same original file directly from your origin server, simultaneously. This surge can instantly overwhelm your backend and cause a catastrophic outage, and the craziest part is, nobody is even attacking you.
So, how do we fix this? The solution is an origin shield. By dropping the shield right between your edge nodes and your backend, all those simultaneous cache misses are consolidated into one single fetch to your origin server. The shield grabs the response, caches it, and distributes it back out to the herd. This drastically reduces your origin CPU load, it slashes those painful egress bandwidth costs, and it completely isolates your backend infrastructure from the public internet.
Which leads us to part 5, the inner vault, or your cloud VPCs.
So, we've filtered the traffic, we've stopped the bots. Now we're in the most secure area of the architecture, the virtual private cloud, where your actual application logic and private databases live. But the question is, how do we strictly control traffic once it successfully reaches this inner vault? Just because a request made it through the outer walls definitely doesn't mean it has free reign inside. We need internal checkpoint guards, and in modern cloud environments, these take 2 distinct forms: broad, stateless network boundaries, and highly granular, stateful instance protections.
Notice the powerful contrast between these 2 guards. First, you have security groups. These operate at the individual instance level, and this is absolutely crucial, they are stateful. That means if they allow an incoming web request, they automatically permit the return traffic back out to the user. On the flip side, you have network ACLs. These operate at the broader subnet level, and they are stateless. They do not remember connections. If an ACL allows traffic in, you literally must have an explicit separate rule to allow the response traffic back out. Also, security groups only use allow rules, while ACLs let you explicitly deny bad IP ranges.
But listen, All of these incredibly powerful tools are completely useless without operational discipline. Specifically, the principle of least privilege. Never ever just allow all traffic from everywhere. Best practices dictate strict whitelisting. For instance, your security group should only accept traffic specifically from your origin shield's IP addresses. You also need to actively mask your origin IP, change it after you set up your CDN, and rigorously monitor your VPC flow logs to catch any internal anomalies or misconfigurations.
All right, let's wrap this all up in Part 6, Unified Defense in Depth.
The true beauty of modern cloud network security is really in the orchestration. Let's follow the spatial journey of one single successful web request. First, it hits the Anycast distribution layer, where volumetric attacks are instantly absorbed on a global scale. Second, it passes through edge filtering, where the WAF strips out those hidden Layer 7 exploits. Third, caching and shielding kick in to prevent a thundering herd. Fourth, as it actually enters your cloud environment, the NACL enforces broad subnet policies, making sure the traffic is coming from a trusted edge node. And finally, the security group provides ultimate granular workload protection right at the server level. It's a gauntlet. If an attacker somehow bypasses one layer, the subsequent layers are just sitting there waiting to neutralize the threat.
Which brings us to a final critical question for you to consider about your own infrastructure. As cyber threats grow in complexity, are you relying on a single wall or a beautifully coordinated multi-layered digital fortress? Because in today's digital battlefield, speed and security absolutely must work as one continuous system. Thank you so much for joining me for this explainer, and I hope this gives you a much clearer view of the incredible journey your data takes every single day.
Coordinating communication paths across massive physical distances is one of the oldest engineering challenges in information technology. Long before modern data protocols, public switch telephone networks solved this routing problem by physically separating the control mechanisms from the voice data. Operators used manual patch cables to dictate the exact physical path a call would take. Traditional data networks largely ignored the separation. In a legacy routing model, every piece of physical hardware operates as an independent, autonomous system. Each router contains its own brain for making routing decisions and its own muscle for forwarding packets. Because this intelligence is decentralized, network administrators must configure each individual device manually. It is an intensely time-consuming process that consistently results in human error, configuration drift, and mismatched security policies across the infrastructure. Hardware-centric networks trade operational agility for isolated risk. A failure in one router rarely takes down the whole system, but it forces network management to remain stagnant and reactive. Software-defined networking reorders this relationship by abstracting the complex routing logic away from the physical hardware that forwards the data. It extracts that decision-making power and migrates it into a centralized, software-based entity known as the SDN controller, or SDNC. The underlying physical devices are stripped of their intelligence. They become a simplified infrastructure layer optimized for a single task, rapidly forwarding traffic based strictly on rules pushed down from above. Exposing the network's functions through APIs means developers can program massive infrastructures using standard code. Telecom operators rely on this programmable structure to dynamically carve out isolated network slices on shared physical towers, simultaneously supporting high-bandwidth 5G mobile traffic alongside low-latency IoT networks. Centralizing network intelligence makes real-time microsegmentation possible, but moving the entire brain of the network into a single controller creates a high-priority target. If an attacker compromises the SDNC, they achieve total systemic control over the entire infrastructure. This diagram illustrates the strict three-tier hierarchy that replaces the legacy distributed model. At the top is the management plane, responsible for administrative configuration and monitoring. It issues commands downward via RESTful APIs across what is known as the northbound interface. In the middle sits the control plane. This is the controller itself, calculating routing tables and actively populating the rules for data flow. At the bottom is the data plane, housing the physical switches that execute packet forwarding exactly as instructed. The critical bridge connecting the brain to the muscle is the southbound interface, frequently utilizing the OpenFlow protocol to translate logic into physical forwarding actions. By replacing physical cables with programmatic trust, the northbound and southbound APIs become the primary attack surface for the entire network. OpenFlow switches in the data plane are built for speed rather than storage. To keep memory demands low, they have a highly limited flow table capacity. An attacker exploits this by firing an intense flood of entirely unique, spoofed packets directly at a target switch. Because the switch lacks its own logic, it has no existing rules for these unknown flows. It must immediately query the central controller for instructions. This generates a massive packet_in message storm, sending thousands of simultaneous queries surging upward across the southbound interface. The incoming barrage quickly saturates the central controller's processing memory, triggering a network-wide denial of service. Attackers routinely target restricted resource IoT devices to build botnets, specifically to execute these volumetric amplification attacks. Overwhelming the memory of a single forwarding node is enough to lobotomize the centralized intelligence of an entire SDN environment. Attackers do not need direct access to the controller to manipulate the network. They can achieve unauthorized reconfiguration by tricking the system's own internal logic. The SDN controller continuously maps the network topology by relying entirely on pinged feedback signals returned from the underlying switches. If an attacker injects forged link layer discovery protocol packets between two legitimate switches, they insert false connection signals into the data stream. The controller receives the falsified signal and miscalculates the map, drawing a bogus physical link that does not actually exist. With the map corrupted, the controller will unknowingly route legitimate traffic directly through a node operated by the attacker, securing a covert man-in-the-middle position. Another attack vector targets the application layer. Compromised third-party applications can interact with the northbound API to generate subtly conflicting flow rules, effectively bypassing firewall restrictions without triggering primary alarms. At the data plane, a compromised node can execute a complete ARP table rewrite, instantly steering outbound traffic into a malicious sinkhole. While modern SSL and TLS encryption prevents the attacker from reading the payload data, they can still analyze the intercepted stream for network reconnaissance or black hole the traffic completely. When the controller's logic is fed poison data, the network reconfigures its own flow rules to serve the attacker. The entire process requires zero physical access to the networking hardware. Securing a centralized architecture requires countering single-point vulnerabilities with distributed, mathematically proven resilience. This equation models controller availability, defining the strict survivability requirements of the control plane under stress. To eliminate a single point of failure, administrators must deploy n redundant nodes operating together in a distributed cluster with automatic failover. Even a redundant network is vulnerable to static reconnaissance. Engineers counter this using moving target defense. Moving target defense dynamically and continuously reconfigures network characteristics, randomly shuffling IP and MAC addresses to blind attackers trying to map the infrastructure. To protect the internal command structure, the NSA mandates stringent cryptographic validation, requiring TLS 1.2 or higher to authenticate instructions sent across the southbound interface. Architectural resilience is achieved by deploying the controller as a cryptographically hardened, decentralized collective. Legacy security measures rely on periodic audits and reactive blocking. These methods are mathematically too slow to prevent automated, high-volume attacks against an SDN. Software-defined networking contains an inherent defensive advantage. The central controller possesses a continuous, holistic view of bidirectional flow records across every network switch. This formula calculates total detection latency, detailing the efficiency required for algorithmic defense. The controller's global visibility minimizes the time required to collect data. It then applies machine learning algorithms to aggressively accelerate the inference time. Algorithms specifically monitor the incoming volume of packet-in messages per port, identifying early algorithmic signatures of DDoS amplification. Identifying malicious floods in under 2 seconds, the controller responds by instantaneously pushing new access control lists down to the data plane to quarantine the traffic. This rapid containment executes strict zero-trust policies and dynamic microsegmentation, cutting off lateral movement before an attacker can expand their presence. Software-defined networking centralizes an organization's operational risk. But by combining cryptographic enforcement and machine learning automation, it creates a self-governing, proactive defense system that replaces the static
Welcome to The Explainer. I'm absolutely thrilled to have you here today. If you've ever stared at dense network security architectures and felt like you were trying to read some sort of alien language, trust me, you are definitely not alone. Today, we're going to translate those complex layered concepts into a crystal clear architectural blueprint. We're going to construct a digital fortress together using the very frameworks and protocols that industry professionals rely on every single day. Okay, let's dive right into this. 13%. That is the massive chunk of the entire CISSP framework dedicated just to Domain 4, communication and network security. It's widely regarded as one of the absolute most technical and demanding segments out there. I mean, this isn't just about plugging in routers or memorizing random port numbers. It is about the strategic alignment of your network design with actual risk management. Our networks are literally how organizations interact with clients and generate revenue. They're the crown jewels. So the stakes for building a defense-in-depth strategy across the physical, logical, and administrative realms are incredibly high. So here's the roadmap for the digital fortress we're building today. First up, the network security blueprint. Next, securing data in transit, followed by building digital walls. Then, we'll cover securing the invisible airwaves, and finally, defeating modern cyber threats. Let's get right to it. Part 1, the network security blueprint, conceptual frameworks. Before we can even think about defending our fortress, we need a common blueprint, right? And the absolute foundation of that is the OSI model. Think of this as our universal risk management framework. If we walk up the stack, starting way down at the bottom at layer 1, we're dealing with raw physical cables and binary transmission. Security down here? Well, it's all about physical access controls, basically stopping someone from literally wiretapping a cable. As we move up through the data link and network layers, we start dealing with MAC addresses, IP routing, and the constant threat of spoofing. By the time we hit layer 4, the transport layer, we're looking at connection states and fending off denial of service attacks. And finally, at the very top, layers 5 through 7, we reach the application realm. That's where protocols like HTTP and TLS live, and where those really complex application attacks happen. This 7-layer model is our common language. It lets us map a specific threat to the exact layer it targets, and then hit it with a highly precise countermeasure. But here's a quick reality check for you. While the OSI model with its 7 layers is absolutely brilliant for conceptual risk analysis, it's not exactly how the internet is built in practice. The internet actually runs on the TCP/IP suite, which consolidates those functions into just 4 implementation layers. For instance, TCP/IP's application layer absorbs the top 3 layers of the OSI model into one. In reality, security practitioners have to be fluent in both. We use OSI to conceptually map out the risks, but we configure our everyday networks using the TCP/IP model. Moving on to part 2, securing data in transit, securing the messengers. Now, this brings up a really fascinating question. Why did the industry recently, and I mean urgently, abandon TLS 1.2? For a very long time, TLS 1.2 was the absolute gold standard for securing web browsing, emails, and API protection. But the threat landscape evolved, and our legacy standards simply had to evolve right along with it. What's really interesting here is how drastically TLS 1.3 improves both speed and security over its predecessor. Take the handshake speed, for example. TLS 1.2 required 2 round trips, or 2 RTT, between the client and server just to negotiate keys. TLS 1.3 slashed that down to a single round trip. It even allows for 0 round trip time for recurring connections, which is just a huge deal for reducing latency. But the security upgrade is even better. TLS 1.3 makes forward secrecy absolutely mandatory. What does that mean? Well, even if an attacker steals a server's long-term private key today, there's no way they can use it to decrypt past traffic they might have recorded. Every single session gets its own independent ephemeral key. It's a massive leap forward. So while TLS is amazing for securing specific application sessions, like browsing a website, what happens when you need to secure an entire network branch? Enter IPsec. IPsec operates at the network layer, layer 3. It's a heavy-duty framework that creates a secure tunnel protecting all IP traffic between systems. While TLS protects an app, IPsec in tunnel mode actually hides your entire internal network topology from the public internet. It encapsulates your original IP packet entirely inside a brand new one. For site-to-site VPNs, this is the ultimate gold standard. Setting up that IPsec tunnel relies on a protocol called IKEv2, which involves some seriously complex math. But we can simplify it into an elegant 2-step process. In Phase 1, the systems authenticate each other and establish a secure bidirectional management tunnel. Once that safe space is created, Phase 2 kicks in. Inside that secure management tunnel, the systems negotiate the actual unidirectional end-user data tunnels. It's kind of like building a heavily guarded hallway first, just so you can safely discuss the blueprints for the rooms inside.
All right, part 3, building digital walls, perimeter defenses.
So the crucial point here is containment. Segmentation limits the blast radius of a breach. If you look at environments handling credit cards, which are subject to strict PCI DSS regulations, they use a robust containment strategy. By isolating the cardholder data environment using virtual local area networks, or VLAN, alongside firewalls, they act almost like submarine blast doors. Imagine an employee's workstation gets compromised by a phishing email in the general corporate zone. Boom, the attacker hits that digital wall. They can't move laterally to steal credit card data. Plus, the strategy significantly lowers the cost of compliance, simply because fewer systems fall under those strict audit rules. Of course, those digital walls are only as good as the gatekeepers manning them, which brings us to firewalls. Old-school, traditional, stateful firewalls operated mostly down at layer 4. They tracked connection states and filtered based on ports. But modern threats, they act like chameleons, hiding right inside allowed ports like 443. That's why we rely on next-generation firewalls, or NGFWs. These powerhouses operate all the way up to layer 7. They use deep packet inspection and application awareness to literally look inside the payload. They don't just see generic traffic on an open port. They can distinguish between a user harmlessly browsing Wikipedia and a user trying to exfiltrate a massive database file over that exact same port. Part 4. Securing the invisible airwaves, wireless security. When our network literally bleeds through physical walls, Wi-Fi becomes our absolute most vulnerable attack surface. For over a decade, WPA2 was the standard, but it had well-known flaws, like allowing offline dictionary attacks. WPA3 finally fixes these vulnerabilities with some massive architectural upgrades. First up, simultaneous authentication of equals, or SAE. This requires an active interaction for every single password guess, completely stopping those offline dictionary attacks in their tracks. Then we have management frame protection, or MFP. This encrypts some management traffic so an attacker can't easily spoof an access point and knock you off your network. Add in an optional 192-bit security suite for enterprise environments and enhanced open to finally encrypt data on public guest networks, and WPA3 fundamentally changes wireless defense for the better. It's a brilliant example of just how much enterprise wireless authentication has matured. Back when users logged into enterprise Wi-Fi with older protocols like PAP, it relied on a standard username and password. The obvious problem? Passwords can be phished, making PAP super vulnerable. Enter EAP-TLS, the new gold standard. It uses mutual certificates, meaning both the server and your device must present a cryptographic digital certificate to prove exactly who they are. Because it completely removes human-entered passwords from the equation, it is literally immune to phishing and credential theft. It is the highest level of security we have available for wireless access. Which brings us to Part 5, defeating modern cyber threats, the attack lifecycle. When an attacker strikes, they typically follow a predictable life cycle. First is reconnaissance. They poke around and try to map your network. But our next-gen firewalls block unauthorized scanning, keeping our topology hidden. Next, they might attempt a denial of service to exhaust our resources and cause a panic. However, our layered architecture handles rate limiting right at the distribution layer to absorb the shock. Finally, they might attempt a man-in-the-middle attack to intercept data. But guess what? Because we've mandated TLS 1.3 on our applications and EAP TLS on our Wi-Fi, the communication is totally locked down with mutual authentication and forward secrecy. The interception completely fails. Let's move on and see how this builds out to our foundational services. Your web and app traffic is secure, but attackers absolutely love to target DNS and email as a sneaky backdoor. We secure DNS using DNSSEC, which adds cryptographic signatures to prevent attackers from poisoning the cache and redirecting your users to malicious sites. For email, we use a trio of protocols. SPF verifies who is actually allowed to send mail on your behalf. DKIM cryptographically signs the message to prove it hasn't been tampered with. And DMARC, it tells the receiving server exactly what to do if those first two checks fail. Working together, they neutralize email spoofing. As we wrap up this explainer, I really want to leave you with a provocative question. Are your microperimeters tight enough for a true zero-trust architecture? As we've seen today, true defense in depth is not just about buying a fancy firewall or turning on WPA3. It's about orchestrating a holistic, highly adaptive strategy across all 7 layers of the OSI model. It is about ensuring every single user, device, and packet is constantly verified, both inside and outside the perimeter. So take some time to review your blueprints, implement those containment strategies, and make sure your defenses are adapting just as fast as the threats are. Thanks so much for joining me on this deep dive, and keep building those digital fortresses.